Today we will study some more definitions, examples and results in topological space. So first definition is adherent point. Suppose X3 is a topological space and A is a subset of X. Then a point X belonging to capital X is called an adherent point of A if and only if every neighborhood of X contains at least one point of A. It means the point X belonging to X is called adherent point of A if and only if there exists a neighborhood N of X such that intersection of N and A is not equal to phi, means it is non-empty. And we denote the set of all adherent point of A by writing ADH and within bracket A. So this means adherent point of A. Now the isolated point. Again, if Xt is a topological space and A is a subset of X, then a point X belonging to A is called an isolated point of A if X is not a limit point of A. It means there exists a neighborhood G of X such that G minus singleton set X. If we remove singleton set X from G, then its intersection of this set with A is empty. Means these are disjoint. Or we can say G intersection A is equal to singleton set X. If every point of a set A is an isolated point of A, then the set A is called the isolated set. Now interior, exterior and frontier. Let Xt be a topological space and A is a subset of X. A point X belonging to A is called an interior point of A if X belongs to an open set G contained in A. It means X belongs to G, which is a subset of A. Here G is a open set. And set of all interior points of A is called the interior of A, and we write it as int within bracket A or A like this. So these are the notations for interior of A. So set of all interior point is called the interior of A. And exterior of A is the interior of complement of A. And we denote exterior of A by writing exterior A. And the frontier of A is a set of points which neither belong to interior of A nor to frontier of A. Frontier of A is always closed. Sometimes we also call it boundary of A, and we denote it by delta A. So delta A is equal to A bar intersection X minus A bar, means intersection of A with its complement, because it neither belongs to interior of A nor to exterior of A. An example to show that the union of an infinite collection of closed set in a topological space is not necessarily closed. Suppose T denote the usual topology on R, and let Fn is equal to closed interval 0 to n upon n plus 1 for all n belonging to n, means n is natural number. So here Fn is a closed set in a topological space Rt. R is a set and T is the topology on R, and it is the usual topology. And Fn is a closed set. Now we will show that union of infinite collection of closed set is not necessarily closed. So how will we find its union? Union n equal to 1 to infinity, Fn is equal to, it is, if you put 1, 0 to 1 upon 1 plus 1 means 0 to half. If we put 2, 0 to 2 upon 2 plus 1, 0 to 2 by 3. And similarly, if you put, if n tends to infinity, so if you divide here by n, it is 1, it is 1, and it is 1 upon n. So as n tends to infinity, it will be nearly 1, but not exactly 1, because here it is 1, 1 plus 1 upon n. If we divide numerator and denominator by n, so as n tends to infinity, it will be nearly 1. So if we take the union of all these, then it will come out to be 0 to 1. So 1 is not included here. So it is a we can call it semi-open set or semi-closed set. But this is not a closed set. It means infinite union of closed set is not closed, although each Fn is closed set. So we have shown that the union of an infinite collection of closed set in a topological space is not necessarily closed. Now one more result. Let A be a subset of a topological space X, then interior of A, exterior of A, and frontier of A are disjoint. Means their intersection is empty set. Also, X is equal to interior of A, union exterior of A, union frontier of A. Further, frontier of A is a closed set. So first of all, we will show that the interior of A, exterior of A, and frontier of A are disjoint. Then we will show that their union is equal to complete set X. And finally, we will prove that frontier of A is a closed set. We know by the definition that exterior of A is equal to interior of complement of A. Also, we know that interior of A is a subset of A. So, in the same way, we can say that interior of A complement is a subset of A complement. So, interior of A intersection exterior of A can be written as interior of A, and because exterior of A is interior of A complement, so we can write it as interior of A complement. But A and A intersection is equal to phi. Intersection of a set with its complement is always a empty set. So interior of A intersection interior of A complement is also a empty set. Also, by definition of frontier, X belongs to frontier of A if and only if X does not belong to interior of A, as well as X does not belong to exterior of A. It means because X is neither in interior A, neither in exterior A, so it is possible only if and only if X is not in interior of A union exterior of A. And this is possible only if and only if X belongs to interior complement of interior of A union exterior of A. So here I have used if and only if sign. So if X belongs to frontier of A, then X belongs to interior of A union complement of interior of A union exterior of A. And if X belongs to interior of A union exterior of A complement, then X belongs to frontier of A. It means frontier of A is equal to interior of A union exterior of A complement. But interior of A intersection exterior of A is empty set. Also, X does not belong to interior of A and X does not belong to exterior of A. So, frontier of A intersection interior of A is also empty set, and intersection of frontier of A and exterior of A is also a empty set. And X is equal to interior of A union exterior of A union frontier of A. Because X belongs to frontier of A if and only if it belongs to complement of interior of A union exterior of A. Since interior of A and exterior of A are open sets, so we can say that because frontier of A is its complement. So we can say that frontier of A is closed set. Interior of A is open, exterior of A is open, so their union is open and complement of open set is closed. So frontier of A is closed. Now we will give an example of a topological space which is different from discrete and indiscrete space, in which open sets are exactly the same as closed set. Suppose X is a set of real numbers and T is the set of all those subsets G of R having the property that X belongs to G implies minus X belongs to G. So it means RT is a topological space which is different from discrete and indiscrete space. So first of all, we will show that this T is actually a topology for R, and this we will show by the definition of a topology. We will show that it satisfies all the three properties of a topology. It is clear that phi belongs to T. Also by definition, we have supposed that if X belongs to G, then minus X also belongs to G. It means R belongs to T, because if any real number belongs to T, then it's negative, then minus X also belongs to G. It means R belongs to T. So phi belongs to T, R belongs to T. So first condition is satisfied. If G1 belongs to T and G2 belongs to T, means G1 and G2 are any two elements of T, and suppose X belongs to G1 and G1 intersection G2. It means because X belongs to intersection of G1 and G2, it means X1 belongs to G1 as well as X belongs to G2. By definition, we have assumed that if X belongs to G, then minus X also belongs to G. It means minus X belongs to G1 and minus X belongs to G2. Because minus X belongs to both G1 and G2, it means minus X belongs to G1 intersection G2. Hence, G1 intersection G2 belongs to T, because for every X belonging to G1 intersection G2, minus X also belongs to G1 intersection G2. So by our assumption, G1 intersection G2 belongs to T. Now third condition, let G lambda belongs to T for all lambda belonging to some indexing set, and let X belongs to union of G lambda. Because X belongs to union of these G lambdas, where lambda is in some indexing set, it means X belongs to G lambda for at least some lambda belonging to indexing set. And by our assumption, it means minus X also belongs to G lambda. And this implies minus X belongs to union of G lambda, where lambda belongs to some indexing set. This is by our assumption. And if minus X belongs to some set, it means it must belongs to their union, and it means union of G lambdas belongs to T. It means if some set belongs to sets belongs to topological space T, set T, and their arbitrary union also belongs to T. It means T is a topology for R. Now we will show that every open set in this topological space is also a closed set. Suppose G is an open set. Now we will show that G is also closed. It means its complement is open, means R minus G is open. Suppose X belongs to R minus G. It means X does not belong to G. It means minus X also does not belong to G, because we have assumed that if X belongs to G, then minus X also belongs to G. But because X does not belong to G, therefore minus X does not belong to G. It means minus X belongs to union of R minus G. It means R minus G is open. R minus G is open means G is closed. So we have shown that RT is a topological space which is different from discrete and discrete space, in which open sets are exactly the same as the closed set. Now we will show that in a topological space an arbitrary union of open set is open and finite intersection of open set is open. Actually, this is by the definition of topological space. Let Xt be a topological space and Gi belongs to T for all I belonging to N. Suppose N means set of natural numbers. Let G is equal to union of Gi's, where I varies from 1 to infinity. Here it is I. And H is equal to intersection I equal to 1 to N Gi. Because Gi belongs to T for all I belonging to N, it means it must belong to their union. So it implies union of, here it is I. It means union of I equal to 1 to infinity, Gi belongs to T. Because union belongs to T, it means we have denoted it by G. It means G belongs to T by definition of a topology. It means G is open set. Because G1, G2 belongs to T, it means G1 intersection G2 also belongs to T by the definition of a topology. So if we apply this rule again, if G1 intersection G2 belongs to T and G3 belongs to T, then G1 intersection G2 intersection G3 also belongs to T. So by fundamental principle of induction, intersection of I equal to 1 to N, Gi belongs to T, and we have denoted it by H. It means H is a open set. So arbitrary union of open set is open and finite intersection of open set is open. This is arbitrary union and this is finite intersection, because we have considered I equal to 1 to N here. Here we have considered I equal to 1 to infinity. In a topological space Xt, an arbitrary intersection of closed set is closed and finite union of closed set is closed. Suppose Xt is a topological space and Fi is a closed set for all I belonging to N. We denote H equal to intersection of I equal to 1 to infinity Fi and F equal to union I equal to 1 to N Fi. This is arbitrary intersection. This is finite union, because here I varies from 1 to N, here I varies from 1 to infinity. We have supposed that each Fi is closed. It means its complement is open, means x minus Fi is open for all I belonging to N. But in the last theorem we have seen that arbitrary union of open set is open. So its arbitrary union means I equal to 1 to infinity x minus Fi, and finite intersection means I equal to 1 to N x minus Fi are open sets. Because arbitrary union of open set is open, finite intersection of open set is open. If we apply De Morgan's laws to these, it means x minus intersection Fi I equal to 1 to infinity, and it means x minus union I equal to 1 to N Fi. We have applied De Morgan's law. It means x minus intersection I equal to 1 to Fi, and it means x minus union I equal to 1 to N Fi, because this union get changed to intersection. Here intersection get changed to union while implying complements. So it means, because these are open sets, it means intersection, this is a open set, it means its complement means I equal to 1 to infinity fi, and its complement I equal to 1 to n fi are closed sets, because complement of a open set is closed. It means this is H and this is F. We have assumed here, it means H and F are closed sets. Now we will show that if U consists of empty set phi and all those subsets G of R having the property that to each x belonging to G there exists epsilon greater than 0 such that x minus epsilon to x plus epsilon, this open interval is a subset of G. Now we will show that U is a topology of R, and in fact this is called the usual topology. We know that the step is almost similar as we did in a previous slide. Now we will show that U is a topology of R. For this we will show all the we will show that the set U satisfies all the properties of a topology. So first is, clearly phi belongs to U by definition. Also R belongs to U. We have considered set of real numbers here. So R belongs to U, because for each x belonging to R, x open interval x minus 1 to x plus 1 is a subset of R. Or we can generalize it. It actually means if 3 belongs to R, if 3 to 4 belongs to R, open interval 3 to 4 belongs to R, then 3 minus 1 is 2, 3 and 4 plus 1 is 5. So 2 to 5 also belongs to, 2 to 4 is also a subset of R. So in general we can say that for every epsilon greater than 0, if if open interval x belongs to R, then x minus epsilon to x plus epsilon is also a subset of R. If x belongs to R, then open interval x minus 1 to x plus 1 is a subset of R. Means if 5 belongs to R, then 5 minus 1 4, 5 plus 1 6, open interval 4 to 6 is a subset of R. So we can say in general, if epsilon belongs to R, epsilon is greater than 0 and x belongs to R, then x minus epsilon to x plus epsilon is a subset of R. This open interval is a subset of R. So it means R belongs to U. So we have shown that phi and R belongs to U. Suppose G1 and G2 are any subsets of U. If G1 intersection G2 is not equal to phi, means if they are disjoint, then there is nothing to prove. Suppose they are not disjoint. Suppose x belongs to G intersection G2. It means x belongs to G1 and x belongs to G2. Hence there exists epsilon greater than 0 and epsilon 2 greater than 0, such that open interval x minus epsilon 1 to x plus epsilon 1 is a subset of G1, and open interval x minus epsilon 2 to x plus epsilon 2 is a subset of G2. Suppose we define epsilon equal to minimum of epsilon 1 and epsilon 2. It means for epsilon greater than 0, x minus epsilon to x plus epsilon is a subset of G1 intersection G2. I have taken epsilon to be minimum of epsilon 1 and epsilon 2. Because this is a subset of G1, this is a subset of G2, epsilon is defined like this. Therefore, open interval x minus epsilon to x plus epsilon is a subset of G1 intersection G2. And this shows that G1 intersection G2 belongs to U. It means finite intersection of sets also belongs to U. Intersection of two sets we have considered, intersection of two sets is also in U. Now we will consider arbitrary collection of members of U. Let G lambda, where lambda belong to some indexing set, be arbitrary collection of member of U. Let X belongs to union of G lambda for lambda belonging to some indexing set. It means X belongs to G lambda for at least some lambda. Since G lambda belongs to U, it means there exists epsilon greater than 0 such that open interval x minus epsilon to x plus epsilon is a subset of G lambda. But then x minus epsilon to x plus epsilon is a subset of union G lambda such that lambda belonging to some indexing set U. Hence, U is a topology for R. This topology is called user topology, or we also call it standard topology or Euclidean topology for R. So we have shown that R with topology U, RU is a topological space because U satisfies all the three properties of a topology. And this particular example shows that notion of topological space is an abstraction of some interesting properties of real numbers. Because in real numbers we considered open intervals, closed intervals and so on. Now relative topology. A topology of a subset of a topological space obtained by intersecting the subset with every open set in the topology of the space. So the topology U of Y, which is a subset of X, is called the relative topology on Y if U is equal to G intersection Y, where G belongs to T, means G is open set in T. We also called it the relativization of the topology T on X. And this space Y together with this topology U is called the subspace of XT. If A is a subset of Y and Y is a subset of X, and in this case, if A is open in Y and Y is open in X, then A is open in X. If A is closed in Y and Y is closed in X, then A is closed in X. So, the relative topology is a topology of a subset of a topological space obtained by intersecting subset with every open set in the topology of the same space. For example, if we consider the topology T equal to T consisting of empty set phi, singleton set A, the set BC, set ABC and X on a set X equal to ABC consisting of 4 elements, and if Y is equal to set consisting of BCD, so clearly Y is a subset of X, then we will find the relative topology on Y. Suppose we denote relative topology on Y by U. Then by definition, U is equal to G intersection Y, where G belongs to T. It means U is equal to phi intersection Y, because here we have phi, A intersection Y, then BC intersection Y, then ABC intersection Y, then X intersection Y, by definition of a relative topology. So, phi intersection Y is phi, A intersection Y, Y is BCD. So, A intersection with BCD is phi. BC intersection Y is BC because it is BCD. Y is BCD. So, BC intersection Y is BC. ABC intersection Y. ABC intersection Y is again BC because we don't have A here. And X intersection Y is BCD, which is Y. X is ABCD, Y is BCD. So, X intersection Y is Y. So, this can be written because phi is repeating here. So, phi BC is repeating here. So Y and BC. So relative topology of Y is phi, is the set phi consisting of, phi, Y and BC. Consider the usual topology T on R and the relative topology U on the set Y equal to 0, 1. Then the open interval 0 to half is U open as well as T open, means it belongs to U as well as T, because we know that element of a topology is called the open sets. So 0 U is just to emphasize on the topology under consideration, and T is also to emphasize on the topology under consideration. Otherwise we can simply write open sets, but here we have topologies. U is different topology, T is different topology, so I have written U open and T open. So here U 0 to half, open interval 0 to half belongs to U as well as T. It means it is U open as well as T open. If we consider semi-closed intervals half to 1, then we notice that intersection of half to 2 with open interval 0 to 1, it is on the set of real numbers and it is phi, is G intersection 0 to 1, where G is this open interval and this is equal to G intersection Y. It means 0 to half is U open as well, half to 1 is U open but not T open. It is U open, means it belongs to U but does not belong to T. So it is U open but not T open. If we consider the open interval half to 2 by 3, then half to 2 by 3 intersection with closed interval 0, 1 is equal to G intersection Y. Here G is half to 2 by 3 and it belongs to U, and also half to 2 by 3 belongs to 3 T. So half to 2 by 3 is U open as well as 2 open. Actually it is closed interval 1 here. It is closed interval 1 here. So here it is closed interval 1. So it does not belong to no, it is fine here. It is half open interval half to 2 intersection 0 to 1. So in open interval half to 2 is this is an open interval in T, but this semi closed interval half to 1 belongs to U but does not belong to T, because we have considered the set of real line and this is not an open interval for the set of real line. And why is this set? So it belongs to, it is U open but not T open. Similarly, if we consider 0 to half, it is closed at half, it is not U open as well as not T open. Because half minus epsilon to half plus epsilon contained in G intersection Y is equal to 0 to half. For some epsilon greater than 0 is not possible. Now base. Let Let xt be a topological space and B is a subset of T such that B is not equal to phi. B is said to be a base for the topological space topology T on X. For topology T on X, if for given a non-empty set G belonging to T, there exists B1 which is a subset of B such that G is a union of B where B belongs to B1. It means a base B for T is a subset of T where each open set can be written as union of elements in B. The set of all open intervals in R form a base for the usual topology on R. The set of open interval Rs with R and S as rational number form a base for the usual topology. Now subbase. Let Xt be a topological space and S is a subset of T such that S is not equal to phi. Then S is said to be subbase or open subbase for topology T on X if finite intersection of the members of S form a base for the topology T on X. It means union of member of X, S give all the member of T. The element of S are referred to as subbasic open sets. Base is also called an open base or basis for the topology. Similarly, subbase is also called open subbase for the topology. Now let X is equal to the set consisting of elements 1, 2, 3 and 4 and A consists of interval 1 to 2, a set consisting of 1 and 2, a set consisting of 2 and 4 and singleton set 3. Now we will find the topology on X generated by the elements of A and the base for this topology. Suppose X is equal to this and A equal to this. These are given to us. So finite intersection of members of A give the class B. We have written these 1, 2, 2, 4, 3. These are the elements of A, and if we intersect this set consisting of 1 and 2 and 2 and 4, the intersection of these two sets is 2. Intersection of 1 and 2 with 3 is phi. Intersection of 2 and 4 with 3 is again phi. So I am not repeating it, and I have considered here X because by definition it is empty intersection of members of A. So this forms a basis for our topology. Now we will construct a topology. We will take the union of members of B. If we take the union of members of B, union of 1, 2 and 2, 4 is 1, 2, 4. Union of 1, 2 and 3 is 1, 2, 3. Union of 1, 2 with 2 is 1, 2. Union of 1, 2 with 5 is 1, 2. This is here. Union of 1, 2 with X is X. Now union of 2, 4 with 3 is 2, 3, 4. Union of 2, 4 with 2 is 2, 4. Union of 2, 4 with 5 is 2, 4. Union of 2, 4 with X is 2, 4. So here it is 2, 4. Union of 3 and 2 is 2, 3. This is union of 3 and 5 is 3. This union of 3 with X is 3. I am not repeating. Union of 5 with 1, 2 is 1, 2. Union of 5 with 2, 4 is 2, 4. Union of 3 with 5 with 3 is 3. Union of 5 with 2 is 2. Union of 5 with 5 is 5. Union of 5 with x is x. Union of x with 1, 2 is x. Union of x with 2, 4 is x. Union of x with 3 is x. Union of x and 2 is x. Union of x and 5 is 5. So this is the union of members of B give us this class. And which is the topology on X generated by the class A. We can check that these elements satisfies all the properties of a topology, and this forms the basis for the topology T generated by the elements of A. Thank you.